It is a pleasure to speak with you today about one of the most important and at the same time most misunderstood problems in investments, asset allocation. For the past 60, 70 years, most asset managers have been using convex optimization methods, whether it is Markovich, Black-Liederman, and other refinements to perform asset allocation decisions, and the results have not been great. The results indicate that, in fact, heuristics such as the 1/n allocation, equal allocation across assets, outperform, out-sample the allocations that come from supposedly more sophisticated methods such as Markovich, Black-Liederman, etc. Today, I'm going to discuss how machine learning can address these problems and help us obtain better performance out of sample. Machine learning is typically discussed in the context of price prediction or execution. And I feel that one very important application that of machine learning that is typically overlooked is asset allocation. Why? Because machine learning can help us derive optimal portfolios by addressing directly the sources of instability that we observe in the convex optimization solutions. In particular, today, I'm going to discuss the two most important sources of instability, that is noise-induced instability and signal-induced instability. You can find the full details of these approaches in my papers and also in the two books that I will show at the end of the presentation. Let's understand first what the problem is. We're trying to optimize a portfolio where we obtain a covariance matrix. This is representative of the codependencies between the various assets. And we also have a vector of expected returns. And the problem that we're trying to solve is how can we minimize the variance of this portfolio while at the same time we obtain a particular target return. The problem could be presented alternatively as maximizing return given a particular level of risk. The two problems are the same. It's just the expression of one versus the other, but the solution will be the same. The approach that typically we follow in finance is we apply convex optimization. Essentially, in the case of equality constraints, we would apply Lagrangian. We would solve the solution with some optimal weights that are the result of the product of the inverse covariance matrix and the characteristic portfolio, which could be the vector of expected returns. The solution for a problem with inequality constraints is going to be different. It will require the critical line algorithm, but essentially the solution looks very similar to this in the sense that it requires an inversion of the covariance matrix and the multiplication of that inverted covariance matrix with a vector of expected returns. Let's discuss the first source of instability of convex optimization solutions, and that is noise-induced instability. To understand that, first we need to realize that the signal-to-noise ratio is very low in finance. This occurs as a result of competition. Many asset managers are trying to extract alpha from the market, and not surprisingly, there is very little information left in this data that we utilize and very little alpha to be extracted. We can quantify the signal-to-noise ratio easily. We can perform an eigenvalue decomposition of the covariance matrix, and what we will see is that most of the eigenvalues in this covariance matrix will fall under the so-called Marchenko-Pastor distribution. The Marchenko-Pastor distribution gives the distribution of eigenvalues associated with a random covariance matrix. So what this tells us is that most of the eigenvalues that comes from a covariance matrix are associated with noise. Very few eigenvalues that you can see here on the right of the plot are associated with signal. again, the signal to noise ratio is very low in finance. And in this case, this exercise is conducted on a covariance matrix that is not empirical. It's a covariance matrix that comes from Barra. So this covariance matrix has already been treated with factors in order to remove some of the noise. But as you can see, even Barra covariance matrices, which are much better than empirical ones, but even Barra covariance matrices exhibit a very low signal to noise ratio. Marchenko-Pastor allows us to determine what is the lambda plus, what is the upper bound of the noise-related eigenvalues. Why is this important? Because applying this method, we can separate eigenvalues associated with noise from eigenvalues associated with signal. And here the boundary is clear around 1.2 or so. How can we use this information? Well, we can use Marchenko-Pastor to denoise the covariance matrix. The procedure follows these steps. First, we identify what is lambda plus. Second, for any eigenvalue below lambda plus, we're going to center them. We're going to replace those values with a constant. As you can see here, on the right plot, the blue line indicates the eigenvalue function before denoising, and the orange line represents the eigenvalue function after denoising. So what we do is once some eigenvalues fall below lambda plus, we're going to replace them with this constant. As the implication is that now the smallest eigenvalues are much higher than before denoising. Why is this important? Because that is the source of instability. Small eigenvalues mean that the determinant of the covariance matrix is almost zero, and inverting a covariance with a determinant of almost zero, of course, means that the estimations of the inverse explode. And if you remember the equation we saw before, to multiply an inverse covariance matrix where the loadings of that covariance matrix are magnified, it just means that any error that we have on the expected returns is going to be magnified. So that is the caveat. That is the main caveat of Markovich, Black-Liederman, etc. That we are multiplying noisy estimates of expected returns with a covariance matrix that when inverted explodes and magnifies those errors. So unless you have some forecasted returns with 12 decimal accuracy, most likely the result that comes out of Markovich is going to be extremely noisy and not robust, with implication that investing in portfolios that are not robust leads to extreme transaction costs. So that is denoising. That helps us address the first source of instability in Markovich. What we're going to see now is an experiment that allows us to estimate precisely what is the benefit that comes from denoising. The experiment follows these steps. First, we are going to generate a vector of means and a covariance matrix that is representative of the market. So we are going to impose some structure. For instance, we're going to impose 10 blocks, each block representative of one sector, and we're going to add a high correlation between the securities, as we observe in the market, where securities, of course, stocks are very highly correlated among themselves, or in the case of bonds are very highly correlated with each other. And so we inject this structure, and then we are going to sample returns from this covariance matrix. The purpose of sampling is that now we want to generate millions of scenarios where we can derive. We're not going to optimize a particular covariance matrix. We're going to optimize millions of covariance matrices, and that is going to help us identify whether the method is robust or not. For each sample covariance matrix, we can estimate the optimal holdings, and then we compare the optimal holdings with the ground truth, the holdings that come from the covariance matrix we started with. This is a Monte Carlo experiment. And this Monte Carlo experiment allows us to derive the mathematical properties of this approach much better than a backtest. A backtest essentially is a historical simulation of a particular covariance matrix, a particular path, and the conclusions that come from a backtest are anecdotal at best. They do not allow us to, backtests do not allow us to derive the mathematical properties of a procedure. Monte Carlo experiments allow us to derive the mathematical properties of a procedure because the characteristics of the covariance matrix are under our control. We can try many different covariance matrices and see if under different inputs, the procedure still exhibits these mathematical properties. In these tables, I'm showing what are the results from Monte Carlo experiments when we apply denoising. On the upper left result, this is the root mean square error that comes from applying Markovitch without any denoising, just taking the bar covariance matrix and running an optimization. As you can see, the root mean square error is relatively high. If we apply a shrinkage, the result is slightly better. There is a reduction in the root mean square error, but the big reduction really comes from applying denoising. In fact, when we denoise a covariance matrix first, and then we apply Markovitch, we obtain a 60% reduction in the root mean square error. Well, we could do both approaches at the same time. We could denoise and then shrink, and the improvement is not much better, meaning that a shrinkage really adds very little beyond the benefits of denoising. Denoising is the key to obtaining more stable results in the context of portfolio optimization. How is denoising different from a shrinkage? Well, it's very different. If you remember a couple of slides before, we saw how Marchenko-Pastor allows us to separate noise-related eigenvalues from signal-related eigenvalues. And this means that we can treat those noise-related eigenvalues separately and effectively without touching the signal. The signal remains unaffected. A shrinkage does not differentiate between signal and noise. It essentially whitewashes everything. And whitewashing a covariance matrix is problematic when the signal to noise ratio is so low to begin with. Essentially, a shrinkage it's not only eliminating a lot of noise, it's also eliminating a lot of signal. And that is why here we see that, yes, there is some benefit to a shrinking the covariance matrix, but definitely it eliminates a lot of the signal. And that's why a shrinkage performs much worse than denoising. I understand that there are many papers in the literature that claim that the shrinkage performs well in historical backtests, and I'm not surprised. You can always identify a particular data set, a particular time period where some technique appears to have worked. Again, backtests only present us with anecdotal information. The only way to determine the mathematical properties of a particular procedure experimentally is with a Monte Carlo experiment, and that's how research is advanced in many cases in statistics, and that's how we should evaluate the mathematical properties of a procedure in finance too. What happens when we repeat this experiment on the estimation of the maximum Sharpe ratio portfolio? Well, here the results are even more interesting. We see that when we apply denoising, we obtain a 94% reduction in the root mean square error. Now, if you're familiar with approaches in finance, typically methods in finance tend to work well or give some additional benefit. It's rare to find in finance an approach where you can obtain a 94% reduction in the root mean square error. Denoising is extremely helpful in investments. It's rarely used, but it should definitely be used more often because the evidence that comes from Monte Carlo experience is very strong that denoising actually is helpful, much more so than a shrinkage. Let's discuss now the second source of instability in portfolio optimization, and that is signal. This is a misunderstood source of instability. 99% of the literature about instability in portfolio optimization deals with the first source. It deals with noise-induced instability. Very few papers discuss signal-induced instability. The reason is that signal-induced instability is not very intuitive at first, but once you think of what is the nature of signals in finance, you realize that there is a problem. Let me provide an insight into why signal can be a source of instability. We all expect that signal is good. This is exactly what we need in order to extract alpha from the markets, right? Well, yes, but as it happens, convex optimization is very sensitive to the kind of signal that we utilize. And in particular, the reason we need Markovitch in the first place is because we are dealing with instruments that are correlated, right? If instruments were uncorrelated, if the correlation matrix was just a diagonal, we wouldn't need a Markovitch. We would just optimize the portfolio by inverse variance allocations. If a security is very risky, it receives less allocation. That would be the case if securities were uncorrelated, but securities are not uncorrelated. And that is why we need Markovitch. The problem with Markovitch is that as soon as there are clusters of securities that are highly correlated among themselves, the condition number of the correlation matrix drops. So the condition number goes up, and as a result, the determinant of the correlation matrix drops. When the determinant of the correlation matrix drops, then the inverse covariance matrix is going to explode. And the reason for this explosion of the covariance matrix is very different from noise. In the case of noise, the instability is related with the sample being too short. Very few observations, therefore the inverse covariance matrix cannot be estimated robustly. In the case of signal-induced instability, the reason the covariance matrix is unstable, it has nothing to do with the sample size. We could work with millions of observations, and still, if the correlation matrix exhibits clusterings, it means that there will be signal-induced instability. You can see this in this plot, right? Essentially, it shows you that there are two main clusters in the investment universe, and then each cluster is subdivided into further subdivided into two additional clusters. So when you apply Markovitch in a situation like this, which is very common in finance because clustering occurs as a result of sectors and countries and industries, etc. When you apply Markovitch to a cluster correlation matrix, what is going to happen is that the signal is going to defeat the purpose of the optimization solution. The optimizer cannot differentiate between securities within each cluster. The securities within each cluster look too much alike, and as a result, just changing a little bit the expected return in one means that all of the weight is shifted towards that security. That is the reason why signal, regardless of the sample size, signal is conducive to instability. What is the solution? Well, the solution is to apply machine learning. We saw in the first part of the presentation that we utilize machine learning to fit the Marchenko-Pastor distribution. And now we're going to use machine learning to address this second source of instability. Let me stress the following. The more we need Markovitch, the more Markovitch is supposed to fail. Meaning that the more non-diagonal the correlation matrix is, the more we need Markovitch. But the fact that the matrix is non-diagonal, because there are clusters, it is going to be conducive to Markovitch failing. So the solution is to apply machine learning to deal directly with this particular source of instability. The procedure is the following. First, we're going to cluster the correlation matrix. You can think of a procedure that is going to identify what securities are more similar to each other, but different from the rest. So that's what forms a cluster. A cluster is going to agglomerate securities that are part of the same sector and similar size. They are very codependent to each other and much less so to the rest. Now that we have some clusters, in the second step, what we're going to do is we're going to optimize each cluster separately. For each cluster, we're going to estimate what are the optimal allocations. By doing so, we prevent that the instability is spread throughout the system, because the instability is contained within each cluster. In the third step, we reduce the dimensionality of the system. If we start with n by n covariance matrix, let's say 1000 by 1000, we identify, let's say, 10 clusters. Now that we know the allocations intra-cluster, we can reduce the system from 1000 by 1000 to 10 by 10. Dealing with a 10 by 10 system is much better than with 1000 by 1000 system, numerically speaking. And in step number 4, what we do is we compute the weights intercluster between the different clusters. So now, instead of thinking about how much we're going to invest in IBM, we're going to think how much are we going to invest in IT. The final allocation is the dot product of the two weights we have estimated. It's the dot product of intercluster weights and intracluster weights. You can see in this diagram how the procedure works. First, you start with some inputs. You may or may not denoise, depending on your analysis. But suppose in this case that we are not denoising. You can partition the variables into different clusters, applying a clustering algorithm. And then for each cluster, we're going to optimize it separately. This allows us to reduce the system and then optimize the reduced system, giving us the final allocations, which is the dot product of the two. Why does this procedure work? Well, there is no mystery why it works. We are transforming an ill-defined problem into a well-behaved problem. When we work with the raw covariance matrix, or even the denoise covariance matrix, there will be clusters that are going to defeat the purpose of the optimization. And instead, what we do is we're going to cluster these securities so that all of these off-diagonal correlations disappear, right? Once we compute the cluster correlated matrix and we reduce the system to, let's say, 10 by 10, now all of the off-diagonal elements are much smaller than in the original matrix. Why? Because if there were high off-diagonal elements, they could be included in one of the clusters. So as a result, the reduced correlation matrix is well behaved, and then we can apply Markovitch. So again, we are transforming an ill-defined problem into a well-behaved problem. That is why this method works. How well does it work? Well, that's why, again, we should run Monte Carlo experiments so that we can reach general conclusions as to how the method works under various circumstances. So again, what we will do is we will begin with a covariance matrix. Let's say one covariance matrix coming from Barra, and we're going to sample thousands of covariance matrices from this Barra covariance matrix, and these are empirical covariance matrices that are derived from Barra. We can optimize each of these portfolios based on each covariance matrix and compare the optimal allocations with the allocations that came from the original covariance matrix, the one that we consider like round truth, the one that comes from Barra. And that allows us to estimate the root mean square error associated with this method. What are the results? The results clearly indicate that this approach is very helpful. When you apply this clustering optimization method to the estimation of the minimum variance portfolio, you obtain a reduction of 47% in the root mean square error. Interestingly, when you apply a shrinkage to this approach, it makes matters worse. So I would warn you against papers that claim that a shrinkage has tremendous benefits in portfolio optimization. Typically, these conclusions are derived from backtests, and backtests are very easy to overfit. It's very hard not to overfit a backtest. And so I'm not surprised that there are some papers that conclude that a shrinkage delivers good results. When you run Monte Carlo experiments, clearly that is not the case. And again, Monte Carlo experiments are the most general approach we can use to derive conclusions. The conclusions that come from Monte Carlo experiments are not anecdotal. They are general. And what happens when we apply both a shrinkage and clustering? Well, in fact, there is very little benefit. Essentially, all of the benefit comes from this cluster optimization. A shrinkage, in fact, should be avoided in the case of dealing with signal-induced instability. And we know exactly why. Why is it that a shrinkage doesn't perform well? There is no mystery. When you shrink a covariance matrix, you are whitewashing a lot of the noise, but you are also whitewashing a lot of the signal. And when you remove a lot of the signal, now the optimization is going to, the optimal portfolio is not going to perform well. Denoising, as we saw before, would have performed much better than a shrinkage. So another calculation here would be to combine denoising with clustering, and that would deliver even better results. The reason I'm not denoising these correlation matrices is because I want to show you the benefit of clustering isolated, so that you can determine exactly, you can see exactly how much reduction in the root mean square error comes just from clustering. How about the maximum Sharpe ratio portfolio? Well, we reach a very similar conclusion, a 55% reduction in the root mean square error. This means money. This means that you are now obtaining a portfolio that is much more robust, is much closer to the true optimal portfolio, and very importantly, it is a stable portfolio. You will not lose a lot of money as a result of transaction costs and market impact. Let me introduce finally a general approach to determine what is the best algorithm you should use for a particular problem. There is no need to rely on a particular algorithm all the time. if we have learned something from machine learning, is that there are algorithms that are better for some particular problems and algorithms that are not so good for other problems. There is no need to rely on regression analysis all the time. Sometimes regression analysis can be helpful, sometimes, very often, not helpful. And the same with portfolio optimization. There is no need to expect that there is some holy grail, some algorithm, some approach that is supreme, that is superior, and that it will always work. That is not the case. Depending on the inputs, depending on the circumstances, some methods will work better than other methods. So the question is, how can we derive what method is conducive to better results in a particular setting? Well, again, we can conduct Monte Carlo experiments to understand what methods are better in a particular setting. We can draw millions of vector of spectrotrons and covariance matrix from a particular input, let's say from Bara, and we can apply the methods to each of these millions of inputs and compare the result with the ground truth that comes from Bara, and see what method would perform better under the assumption that Bara or whatever other source happens to be correct. So again, we are deriving what method is most robust. We're not deriving what source is best, right? The purpose of this experiment is not to derive whether a particular data vendor is better. The purpose of this experiment is, given this data vendor with variables and observations that have these particular patterns and characteristics, what method would perform best under the assumption that this input is correct? So it's a statistical test. And what we can do is we can run this procedure through all these various different methods and evaluate what method is most robust given this particular data structure. So I like this approach because it finally frees us. It frees us from relying constantly on backtests. If COVID-19 will change finance in many different ways. And to me, the most obvious way in which COVID-19 changes finance is that we recognize that historical backtests are very limited. In an environment of zero interest rates and a pandemic, a disruption on the economy, where we have tremendous amounts of unemployment, shocks to the demand and supply, backtests are not helpful. There is no regime in history where we have observed this combination of circumstances. Not the Great Depression, not the Spanish flu. We live in a different economy, and there is no reference that we can utilize for historical backtests. That is why Monte Carlo experiments are so critical today. And again, I understand that 99% of research relies on historical backtests. The results that come, the conclusions drawn from all of that research is not really relevant in today's world. We live in a new world where we need to perform Monte Carlo experiments to derive conclusions, where we understand what is the data generating process and where we are able to evaluate how a method is going to work under various assumptions. I hope that you enjoyed this presentation. If you're interested in the details of these approaches, I invite you to read these two books, Advances in Financial Machine Learning and Machine Learning for Asset Managers, where you can find code and the mathematics behind all of these methods.